So welcome to the seminar today. And our speaker today is Matthias Kaminski from University of Alabama. And so he has worked on various interesting things in the fluid gravity correspondence. He was one of the first to set up the effective action formalism for from where one can get hydrodynamics or equilibrium partition function formalism. He was among the first to set it, and also to get this non-trivial coefficients, this transport coefficients, the chiral transport coefficients, non-dissipative ones at first order related to this quantum anomalies. So today he would be talking about his new work in the field of spin hydrodynamics, which is a very new emerging topic in the field, and so we are very interested to what he has to say about it. So over to you, Matthias.
Thank you, Ayan, for the invitation. Thank you, everyone, for the invitation. I understand this is the seminar channel, The Dual Mysteries of Gauge Theories and Gravity. I will mostly talk about gauge theories, and Ayan said that's okay. I will also comment a little bit on holography towards the end, but I think in order to understand the problems that are there at the moment, it makes sense to approach it from the gauge theory side. So mostly gauge theory in this talk. Again, thank you for the invitation. Very happy to see all of you here. The talk is going to focus on what you see in the picture. This has to do with something with the hydrodynamic regime of certain field theories, and we're going to be interested in spins. So particles that have, like quarks, for example, or some hadrons that have a spin 1/2. For example, and that can interact with the fluid. And so the question is, how do they interact with the fluid exactly, and how do we describe this theoretically? I'd like to convince you that there are some fundamental questions that are important to answer there. And so I'll do that in this context of the relativistic spin hydrodynamics that we have developed in this first paper with Masaru Hongo, Shugang Huang, Misha Stefanov, and Tuang Yi. And I'll comment a little bit on rotating fluids and holography, which is the second paper. So the one thing that you might notice or might have noticed is that there's this word with torsion, and I'll motivate why we would want torsion in a setup that includes spin and hydrodynamics. So again, at any time you have questions, you can stop me or accelerate me, direct me however you wish. Here are my collaborators. Shugang is at Fudan, and Misha, Hoang, and Masaru are in Chicago. And my former PhD student, Marcus Garbiso, is going to be in China soon in postdoc. And right now he's still with us. And Casey Cartwright and Marco Knipfer have also worked on these topics with me. Both of them are my PhD students. All right. So the outline for today is I'd like to introduce spin in heavy ion collisions and mention also how spin appears in condensed matter physics in order to illustrate that there are regimes of these two example systems and the experiments that are conducted there that give rise to hydrodynamic behavior and that give rise to the need to understand spin in such a hydrodynamic regime. So that's going to be the introduction. Spin hydrodynamics is going to be the topic of the section where I'll outline basic ideas and basic concepts. Again, if you know all of that, please let me know, and then we can skip through things faster. And or otherwise, just slow me down if I forget to explain something that's important. We'll construct this form of spin hydrodynamics that I've been advertising in a systematic way. And then this formalism will have to include torsion, and it will be a first order formalism. So we'll talk about that. And these results in the third section are mostly constitutive relations coming from this spin hydrodynamic construction, constitutive relations for the spin tensor, for the spin current and for the energy momentum tensor. And then Kubo relations for the, basically one particular novel transport coefficient that will emerge, and that's called the spin, that's called a shear, the rotational shear viscosity. or rotational viscosity, if you will. We'll talk about that. And then I'll mention that, or discuss that to my mind, this is a very fertile ground for holography, because holography is very good at answering very fundamental questions and answering basic questions, and getting it right, because there's less guesswork when you have an actual holographic model where you can calculate things. And so that is why I believe holography will be, even if it's not QCD, right? It's not the dual to QCD that we will be working with. Even if it's n equal 4 super Yang-Mills, we will be able to answer fundamental questions that will push the field forward in all these areas. So this is my main message. Holography has something to say about this. In the beginning of this month, November 1st through 5th, we participated, or we talked about these topics in this conference, which is the 6th International Conference on Chirality, Vorticity, Magnetic Field, and Heavy Ion Collisions. So I've already.
Sorry, Matthias, I have a question about your previous slide, if you don't mind. Could you explain the picture on the right?
Well, the picture on the right is just my master plan for the talk. This is the Roadrunner. If you're familiar with these comics or cartoons, this is the coyote. This is the Roadrunner. If it doesn't show on your resolution, here's a cliff somewhere in the Grand Canyon area, and this is an anvil. And this is basically the master plan to trap the Roadrunner and have a good dinner. That's the coyote's plan. So my plan for now will be to derive a version of spin hydrodynamics and then have a nice dinner. Have good results with that. And like the hope is that everything goes well. But usually we know that the coyote has some flaw in the plan, and the Roadrunner is smarter than we think. And so hopefully that is where there's the point number 4, holographic ideas, which saves the day for everyone. Well, for everyone but the Roadrunner. Okay, good. So that's the
anyway,
idea.
too early for dinner, right? For you, it's too early for dinner.
It is way too early for dinner. I'm still, yeah. I'm happy with coffee at the moment. But yeah, good. Thanks for the question. So what I tried to describe to you is that there was a big conference, right? So in the beginning of this November of this month, and with about over 200 participants, and this is the 6th incarnation of this topic. So it's a very focused topic on in the field of heavy ion collisions. So these topics, both magnetic fields and the related effects, and then chiral effects, as Ayan had already mentioned, chiral anomalous transport effects are being discussed there, especially the chiral magnetic effect, how it can be measured, how it might have been seen already in heavy ion collisions, and then chirality and vorticity in general. So vorticity is the keyword here for us, because that is a big topic area, one of the, I would say, 2 big topic areas of this conference here. And the vorticity is connected to the spin of certain hadrons, and that has been actually measured. So what people have seen recently, and I'm taking a lot of the information that I have about the experiments from slides to illustrate this from Michael Lisa, leading experimentalist at the STAR collaboration. So you can find his slides in this link at the conference. So what is thought to happen in spin in heavy ion collisions is that you have these 2 heavy ions colliding. And as you see, they overlap in a certain region. So one is traveling this way, the other one is turning that way, indicated by these spheres here. And then what happens in the middle is what we probably all know or have seen at some point in our career is there's this formation of this quark gluon plasma, a bunch of blues and red and green bubbles indicating there's quarks there and there's gluons. And so this is what the basic idea is. That is nothing new, but the idea now is that when you have a non-zero impact parameter, then you know that you can calculate R cross P, like an angular momentum for this whole reaction. So previously the question was how much of that total angular momentum of having a non-central collision but an off-centric collision, having a non-zero impact parameter, non-zero distance between the centers here, of the two colliding nuclei, how much of that angular momentum is actually remaining in the quark-gluon plasma. So we find now, and we will see it in a little bit, we find that there is actually some angular momentum left in the, transferred into the quark-gluon plasma. And not all the momentum or angular momentum is carried away by the remnants, by the spectators which are sitting here. So quite a good amount of angular momentum remains here. And you might think of this in different ways. You might think of this as a shear that is occurring. So the outer layers are traveling maybe a little bit faster, have a bit more momentum than the inner layers. So you have this shear profile here. Oops. Or you might think of it as just two rigid objects that scrape each other, and then like whatever results in the middle is spinning. And so you have at least you have a global angular momentum. And experiments can actually now also distinguish the global angular momentum from local angular momentum. So we believe that there's actually not only a global angular momentum, but also locally there's vorticity. It's a highly vortical fluid. So lots of little eddies, like in a river with like a white water rafting kind of river. So that's the picture that presents itself experimentally. And I can give you a little bit of more data here. You see the same picture that we've just looked at on the previous slide on the right. And now continuing here, we see that depending on the collision energy, that's measured in GeV, there's the polarization of certain particles which happen to be lambda hyperons. So that's an up and down in the strange quark. So it's a particular type of hadron. These guys are electrically neutral and they have vanishing isospin. And they're antiparticles, the anti-lambdas. So it is possible now to measure these polarizations of certain hadrons, and in particular these lambdas, in, for example, Star and Alice experiments. And what you find is that this polarization increases if you go to lower energies. So if you follow, for example, the Star data for the stars here, obviously, the Star data that is indicating the lambda polarization, it increases towards this order 1 giga-electron volt collision energies. And so this is something new and something interesting, because previously the collision energies were much higher, and so one could already see a 1% polarization, but now it became very clear that there's even more happening as you go to lower collision energies. Why is that? Well, the idea is the picture that people have, the physical picture, that when you have very fast collisions, very high energy collisions, most of what remains in the center, in the quark-gluon plasma, is actually generated from vacuum. So basically, you just have energy that is there, C quarks and C gluons. Like you have stuff that comes from vacuum, and the vacuum has no angular momentum. Basically, these two heavy ions pass by each other with a lot of energy and take all of that momentum with them in their remnants. And what's created in this pass by is pure energy, or comes from pure energy. And so that's the idea. And so the lower the energy, the collision energy, the longer these two heavy ions remain there and impart their momentum onto the angular momentum onto the quark-gluon plasma. That's the idea. That's the picture that we have here. And this is also what what is confirmed by Alice and by Star in these pictures here. Alice operates at higher energies, as you see. So this is what goes under the name of lambda hyperon polarization, and it indicates a highly vortical quark-gluon plasma, both like a global angular momentum and a local high vorticity. The equilibration of spins is assumed to be phenomenal, to be perfect. So the idea is that spin is equilibrated in these situations, which is, well, debatable, but it's just the best I would argue that at the moment one is able to do. So fundamentally, spin is not conserved. We know that spin it's just conserved as part of the total angular momentum. So the total angular momentum is the orbital plus the spin angular momentum, and so it is difficult to argue about spin equilibrating and such. And but the idea is these phenomenological models are getting like getting into the ballpark of the data. So, but you will see that this, as you see this red curve here, that's a free fluid model. It's containing two different equations of state, one before the chiral phase transition and one after, or like the confinement transition. This is more like a phenomenological fluid model, not so much a grassroots hydrodynamic construction. This is a carton transport model, and it hugely underestimates the effect at low energies of the polarization. There's chiral kinetic theory calculations which lie in the ballpark of the results here, but we have no understanding of this area. And then there's quantum molecular dynamics, so another kind of like parton or particle model, particle dynamics model, which gets this area right. But this is interesting at low energies, what happens really. So lots of work has been done in these phenomenological models, and they have been gotten much better, and can describe at least part of the data. But there's still a lot of theoretical work needed, because there's still a lot of unclear things. So for example, the sign of the longitudinal polarization is unclear. So if you look in this collision here, if you look, this is the beamline, and if you now look at the transverse plane, transverse to the beamline, you can identify different sectors of polarization. And if you use these models, then they get the sign wrong to begin with. So what you have to do is you have to assume that the temperature gradients vanish. So your temperature is at a certain decoupling temperature, it's constant. And you have to assume that there's a dominant contribution from one particular term, so to say, in the constitutive relations, which is a certain thermal shear, if you term, like if you want me to put a name to it. So it is, but it's rather unclear why one should favor that term and why the temperature should be constant. And so there's a lot of unclarities there. And this is again all very phenomenologically motivated, fitting the data.
Matthias, can I ask something? Sorry, yeah. Can I ask something about this models? So how do they take into account the center of mass energy? Is there some matching involved at some initial stages with some color glass condensate?
Yeah.
Or...
Yeah, I mean, there's always matching. So you can imagine this as color glass condensate is often used, as you said, as you named it, as an initial state. And it's always this picture, right? So you have a heavy ion collision, you have some fluid, and it has certain properties like a vorticity is what we're after here, or a temperature. And you have to model that in some way, because what you detect are the hadrons eventually, and the hadrons carry charges and momentum and a certain energy. So what you detect in your calorimeters eventually is what you know. And so what do you do? How do you bridge the gap between when they collided and what you detect in the hadrons? And this is the models that I'm pointing at here. So yes, I mean they make assumptions. They make a lot of assumptions about you have to start with some sort of initial state. There's assumptions about what is the symmetry, is the geometry of those initial state of the initial ions that collide. That will all have effects on all these quantities. But the point is, yeah, I mean, when they run these models, then to bridge the gap between the collision, the moment there's the collision and the plasma is formed, and the freeze out that happens and hadrons are formed. So that is the unknown, right? So that's the unknown territory, and they do their best. They have a lot of good experience with previous collisions, so can narrow down these models quite well. But yeah, I mean, there's definitely an initial condition that goes in, just like in the standard hydrodynamic modeling that you might know in order to understand eta over S, the shear viscosity over entropy density ratio. So all of that like uncertainty goes in there, if you will, if that's the question that you asked.
Yeah, thanks.
So what you know at the end of a hydrodynamic evolution is the energy momentum tensor and currents, right? Conserved currents. And then from that, you use Cooper-Frye freeze-out equations to translate those into the yields of these particles. And so this is the level at which this modeling happens pretty much. Some of these models take into account the hadron phase in terms of like particle kinetic models. But yeah, we have to bridge the gap where we're blind and we have no data. That's the idea. So another theoretically unclear point is as basic and as fundamental as just the spin currents definition. So that it turns out that the spin current can be defined in different ways because the spin current, if you're familiar with the Bell-Infante or Bell-Infante-Rosenfeld energy momentum tensor, it contains ambiguities because you can perform Bell-Infante transformations, which leave the equations of motion unaffected, but which clearly change the definition of the currents in the energy momentum tensor. So for example, Bell-Infante trick is often used to take a non-symmetric energy momentum tensor and then make it symmetric by these Bell-Infante transformations. This goes under the name of pseudo-gauge transformations in the context of this of the lambda hyperon polarization and spin hydrodynamics. So that's what this refers to. So something as fundamental as the definition of this correct spin current is ambiguous. So that tells you that there's fundamental theoretical insight that we could gain here, and that some fundamental theoretical description is missing. So let me, after this lengthy introduction, just offer such a description. I will, since we're already a little forward in time, I will not talk about this slide in condensed matter physics. Let me just throw two buzzwords at you, and like one is spintronics. That's certainly where people consider spins, spin electronics, that is. So you work with spin instead of only with the charge of electrons, and so that way you can influence how they conduct, how certain materials conduct. So it's spin-dependent conductivity is kind of the keyword, and that leads to also what was honored by the Nobel Prize in 2007, giant magnetoresistance. So basically you can create resistivity by aligning the spins in a material the right way with the help of magnetic fields. So this goes under spintronics, and obviously this has a lot of applications in building storage devices, and is being already used to build storage devices. And eventually the hope is that this also leads into the direction of quantum computing. The one important thing that maybe to take away from this slide, and I'll not mention any of the other things on here, the one important thing is that the total angular momentum is conserved, but there's a coupling between the spin angular momentum and the orbital angular momentum. And so at any given time, you can have angular momentum being transferred between the two. And the transfer from spin to orbital spin angular momentum is usually not dissipationless, but that's a dissipative process. So makes this whole idea of creating a spin hydrodynamics and defining a conserved spin current, or even just a spin current, makes it difficult, right? Because it's entangled with the orbital angular momentum. Okay, so this is you can ask me maybe after the talk if you want me to explain more about this, but this was my introduction of why I think there's a lot of basic questions that need to be answered. There's experimental need to get a better understanding of the experimental results that we have, and we might be able to propose some new devices and some effects in the realm of condensed matter physics. So my proposal here now is, let's construct a version of hydrodynamics that takes spin into account and create that purely from symmetries. So this is emphasized from symmetries. That's what I would like to do. I will let you know to what extent we have achieved this and where the caveats are. So,
can I ask a question?
Yes, please.
Yeah. So you said the conversion of spin to orbital angular momentum. Yeah, this happens at dissipation level. This dissipative effect.
Well, it's okay. I should be more careful. So it's basically connected, right? So spin and orbital angular momentum are connected in this way. I could also write this down as a 3 tensor, which is a generator for Lorentz transformations, and then you have the spin part here, and then here you would have the energy momentum tensor and part in there. And so at any level, like that is not a statement about orders of derivative expansion or where the dissipative parts are or where not. I just wanted to say that also the transfer from spin to orbital angular momentum is also dissipative or can be dissipative.
But so what I wanted to ask was the interactions which may lead to this transfer from spin to orbital angular momentum. So do you, for example, do we necessarily have to have magnetic field, for instance, or the interaction could be something which can be internal?
Well, maybe that becomes clearer when I show you the QCD Lagrangian, because there it happens. We do have that effect in standard theories, quantum field theories with fermions. So you don't necessarily need a magnetic field for it.
Oh, okay.
So maybe it gets a little clearer when I get more explicit.
Okay. Yeah,
but yeah, I'll try to remember your question and address it at the point. Thank you. Okay, let's be a little more concrete. Like, so what do I mean by hydrodynamics? So I mean a theory that answers the question, which are the relevant quantities in a system near equilibrium, and how can we predict their behavior? So basically, I'm asking not about this area here where there's a lot of stuff going on, but I'm pointing at the far region, at long wavelengths, late times, how the ripples here die down. That's what hydrodynamics describes. So we're near equilibrium here after waiting a long time. This is in that sense an effective description at late times and large distances. It's a theory of conserved quantities which survive after that time, because the reason why they survive is that they're protected. So for example, imagine I place a charge density here, like this is like an excess of positive charges. They cannot disappear because they're conserved, right? So they have to do one of two things, like they have to either find something to annihilate with, positive negative charges. So those negative charges have to come from somewhere that takes time, or they have to somehow diffuse. So this positive charge lump has to diffuse in the medium. So that is because it cannot just disappear, because we know it's protected by a conservation law, charge conservation. And so this is why conserved quantities survive at late times, and that's why hydrodynamics is really a theory of conserved quantities. And these quantities take a long time, these charges take a long time to relax. It's like they have a very long relaxation time, infinite relaxation time in the hydrodynamic limit. So this leads to a theory in more technical terms of small gradients. So your gradients cannot be too large. Why is that so? Because gradients are a measure for the time scale in your system. So think about how you express any perturbation of your system, like the little ripple here, or the charge distribution that I mentioned. It can be Fourier expanded if you have a system with translation invariance. So then Fourier modes are eigenmodes, and so I just expand everything in Fourier modes, and the time part of the Fourier transformation is this. So this is representing my little ripple here, my little charge distribution has this kind of behavior with time. This is true if I have translation invariance. And so then any time derivative acting on this little ripple or this little charge distribution will create a minus I omega here. So any time derivative is on the order of what minus I omega is, on the order of the frequency omega of that fluctuation. And so what is the small gradients limit is when this fluctuation frequency is much smaller than the temperature. And so that's the time gradients, and then also the spatial gradients. We want the wave vector to be much smaller than the temperature. So it's a large temperature theory. Hydrodynamics is in that sense. And so the idea is for all these fluid cells that are used to describe this in hydrodynamics, each fluid cell has a certain temperature and depends on time and space. But the neighboring fluid cells should have very similar temperature, such that these gradients are small. Okay, so that means that we have a small gradients in there to begin with, and that's what hydrodynamics then describe. And these small gradients then over time, they relax. They are driving this. Usually the system is driven to uniform temperature, for example. Now, why did I take some time to describe this? Well, because timescales are important in spin hydrodynamics. Because now consider spins, throwing spins into this fluid. Spin is not a conserved charge. So it's not as easy as saying, well, it's protected by a conservation law, so the spin will have to go slow. It's distributing slowly, the spin charge. No, it can immediately transfer itself into angular momentum. And basically the spin charge disappears from the point X where I was just looking. So that makes it possible for the spin to be fast. So I have let's say I have a bunch of spins that are pointing in a certain region of a material, or in a quark-gluon plasma, I have a bunch of quarks that point in one direction. So I have a polarized region, let's say positively polarized. It can immediately, instantly disappear by transforming that spin angular momentum into orbital angular momentum. And that's something new. That's something that we usually don't consider in hydrodynamics, because these modes are fast and they decay quickly. So the point, however, is that spin, by all observations and by all understanding we have, is a slow variable. So spin relaxes slow enough to survive for a long time in order to play along with the hydrodynamic modes. So it survives long enough to be part of the hydrodynamic description, and that's what the type of hydrodynamics that we created, or that we constructed rather. So if you think about it in terms of a dispersion relation, you have your hydrodynamic modes which have a certain wave number here. We know that the hydrodynamic modes at 0 wave number are gapless. They have 0 frequency, 0 energy. That's this axis here. And so you have, for example, these shear modes. That's the red example. And what's plotted here is the absolute values. So this is why this might look a little funny to you, but this is the shear dispersion relation. And this is the blue line is the sound dispersion relation. You see, like this is just a linear dispersion relation, right? Just the speed of sound is the proportionality constant here. And so then that's our pure hydro regime constitute of this. But then there's these green modes here, and these are the spin modes. They come in at this frequency scale or the energy scale on the order of the spin relaxation rate, which we will call gamma S. And this is our spin hydrodynamics regime. So when we include these modes here, which are gapped actually by the amount of the spin relaxation time, or like the inverse of it, the spin relaxation rate. So they are gapped, but they are close enough to the hydro modes. This gap is very small. So we take them into account. And this, if you have heard about this method of spin hydrodynamics, of Hydro Plus that people have been advertising, Misha Stefanov, for example, and Yekin. So that's the idea. So if you're familiar with that, fine. This is very similar to the idea of Hydro Plus. Then all these other modes that are there, that are fast modes, that have a fast decay, they are other non-conserved quantities besides spin, and they disappear fast. And that's why they're not part of our spin hydrodynamic description. But in the regimes that we're interested in, spin survives long enough so that we have to take it into account in the hydrodynamic description. That's the idea.
Matthias, can I ask something about this picture?
Of course.
So could there be that this spin mode and the spin relaxation mode and the shear mode they actually cross? Is there a possibility of that?
Yeah. So it actually happens in models like this. So like for example this here, this crossing. So there's the spin mode here, that's the green mode, and then here's the sound mode. So that's the spin mode, and this the spin mode becoming slower at this wave number than the sound mode, and that in principle that can also happen with the shear mode. I don't at the moment I don't see a. Maybe you have something in mind that would prevent that, but at the moment I don't see.
No. I was just simply thinking that it's more natural interplay because the shear also has some spin right. One associated with
right.
it.
So maybe I should say these are actual. You will see that these are in a few slides that these are actual eigenmodes of spin hydrodynamics that are drawn onto this graph. This is not just wishful thinking. So this shear mode happens to avoid the spin mode in this way. Both spin modes, like the parallel one. There's one parallel momentum, and there's one transverse momentum. And so these two spin modes they are avoided by the shear mode in what we have so far. But that's I don't see a fundamental reason why the red line couldn't cross. Yeah, that's true. And that happens in other systems where like some sort of hydroplus setups, and then you analyze the eigenmodes and the dispersion relation, and you see crossings all over.
Yeah, so there are always instances like in quasi-hydrodynamics, you have the shear, the diffusion pole, and some Drude-like relaxation pole merging, and then you create a K gap. They fundamentally change their nature. So I was now, if you bring angular momentum or spin into business, you can also. So one way to think about spin could be something like a pseudo Goldstone or something with a spin or something like that. So in that case, it might have much more interesting interplay.
That's so in a certain sense, you're talking about like an emergent spin gap. I would argue, like that's maybe
exactly
phrase it, right? So like this gap here, as thinking of it as being the result of some dynamics and well, I mean, I see that, like, and you mentioned the quasi hydrodynamic framework. So I basically what I was describing is hydroplus, and also this version of spin hydrodynamics is a version of quasi hydrodynamics, as far as I understand it. You know more about that than I do, but yeah. So I think it would be it has a resemblance, the way that this mode structure looks like. It looks similar to what happens when you introduce a strong magnetic field in hydrodynamics. So the strong magnetic field does many things, but one thing is it provides a scale which creates a gap. So some of the spin one modes, the shear diffusion modes, they are gapped because of the magnetic field. And so I believe that is such an example of quasi hydrodynamics also. So yeah, definitely there's plenty of examples where that happens. And maybe it would be nice to think of spin as such like a Goldstone generated somehow by this gap being generated somehow dynamically. That's a good, I haven't thought about it that way. Okay, thank you. Yep. So I hope I convinced you now that spin is a little bit different than other conserved quantities, than conserved quantities. So let me motivate two basic ideas here. So one, I mentioned that it is kind of difficult or unknown what the basic definition of the spin current is. So I mentioned that in initial slides, and this is my answer why we want torsion. So let's consider the geometric definition of our currents. Let's say here's a energy momentum tensor as one conserved current, and also a spin current. And how would we define them with the help of a curved metric? Well, we would think of the energy momentum tensor as the source for curvature, right? So if we look at the energy momentum tensor in that definition it's given here, it's some generating functional varied with respect to the metric. That's how we would do it. There's a factor of 2 because of the symmetrization, the indices, and then you have a square root minus g sitting here, which makes this a tensor instead of a tensor density. So, and then you can in the end evaluate this in your favorite space time. Usually we choose the flat space term atom afterwards, because that's what we're interested in, like energy momentum tensor for theory and some theory in a flat metric background. So this variation is how we define this and current. Now let's think about the same geometric definition of the spin current. So we could think of it as being the variation of the generating functional gamma with respect to the spin connection. So that gives it 2 local Lorentz indices, which I indicate by AB with hats, and a coordinate index mu. So it's a Lorentz vector and it's a local Lorentz 2 tensor, if you will. That's what the spin connection is, and that's also what the current is, the spin current. And then, so now my advertisement, why would I want non-zero torsion? Well, if you look at the first order formalism where you have this first carton equation, you see that the metric is not an independent source from the spin connection unless you have torsion. So spin connection is slave to the metric at 0 torsion. How is that? Well, here's my torsion. That's my torsion tensor. Here's my covariant derivative of the Vielbein. So just as a reminder, the Vielbein is if you contract 2 Vielbeins with the flat metric in local Lorentz coordinates, that's the eta AB. Then you get the metric that we were referring to here in the second order formalism. So now we know now that all the metric information is in the Vielbeins by this equation. And we see by the first carton equation, we see that if we have the torsion vanishing, then the Vielbein, at least its derivative, is directly related to the definition of the spin connection. So I can rewrite this and express the spin connection entirely in terms of the Vielbein if the torsion is 0. So that would make my spin connection dependent or slaved to the metric. And so in order to have 2 independent sources, one for the energy momentum tensor and one for the spin connection, the idea is now introduce torsion. And this is just then consider non-zero torsion. This promotes the spin connection to an independent source. And that now is a unique definition for the spin current here. And in the end, we can set torsion to 0, just like we set the metric to a flat metric in the end. Okay, so this is the proposal and it's the motivation why we would work in the first order formalism with torsion. So, well, where does that bring us? Well, let me describe first what we need to do in hydrodynamics in order to now construct this hydrodynamic expression for the spin current and for the energy momentum tensor. And then I'll mention how to do that in first order formalism. So I'll go step by step. So just a quick reminder, again, hydrodynamics is an effective field theory. It is an expansion in gradients of fields. So we need some fields, some hydrodynamic fields. It's a systematic construction, systematic in the sense of it's a derivative expansion. That's what this idea was. What we will systematically construct are constitutive equations for the energy momentum tensor and the spin current. And one can say historically, this has been phenomenologically started on the basis of some phenomenological expressions for the constitutive equations. So this was not really constructed or derived in a certain sense like we nowadays construct effective field theories. It was a bit more phenomenological. That was where it started from. That's the history of hydrodynamics. So let's stick with that idea and see what these constitutive equations are, and then talk about what the conservation equations are and what sources are. So we will need sources. So let me just scroll back. sources is what I mean. Background fields is another way to say it. So the metric is one of these sources. And then we will see that the spin connection now is also a source. So this is what we will do. And so let me give you a few examples. What are the fields that we're interested in? So there's the temperature field, space-time dependent, the charge density, if we have a conserved charge. And there's the fluid velocity, which is also a field, a function of x. The constitutive equations, I'm just giving you the ideal current plus some derivative corrections. So just just to have something on the slide as an example. This current might be conserved. So if you take the leading order contribution, the ideal hydro, it's satisfying a conservation equation. The divergence vanishes, and this can be rephrased physically. This is the continuity equation, right? Any charge change in the charge density in some region, that needs to be a current out of that region, a divergence. That's what this continuity equation says. And then there's the sources, which I mentioned. The metric is something familiar to us. The gauge field is familiar to us as the source for the gauge currents. And then now for the spin currents, we have the spin connection as the new source that we introduce. So that's the new part. So now how do we go about constructing hydrodynamics? Well, it's a three-step process, really. We start with the constitutive equations, and we write down all possible pseudo-vectors and vectors and pseudo-tensors and tensors, which are transforming in the right way under the Lorentz group. So just examples, what needs to go in. For example, here's a scalar that is first order ingredients, the divergence of the fluid velocity. Here's another example, the vorticity. Notice that this is not the omega, that's not the spin connection, this is just the vorticity. I should have used a different letter. So look at the right-hand side. This is the tensor structure that I mean. It's a first order ingredients quantity. That's what I mean. It's the vorticity of the fluid velocity. That's what this is. Just an example of what goes in. So this would contribute potentially to a vector current, or actually to the axial vector current. So here's the second step. You can restrict some of these tensor structures that show up then in your most general constitutive equations by conservation equations. So at zeroth order, we already saw the continuity equation that relates the time derivative of the charge density to the gradient of the or like the divergence of this fluid velocity. So we can simplify some of these tensor structures using conservation equations. And then the other big thing is that we use the argument of local entropy production, the positivity of local entropy production. So this is the local entropy current. So in each fluid cell, we require this divergence to be larger or equal to 0. And that gives us the most general hydrodynamic constitutive equations, which we might also think of as one-point functions. Because once we have them, then we can calculate, for example, we can vary them with respect to the sources. Remember the metric and the spin connection and the gauge field. They are sources in this formalism. And we can now, once we have these generally constructed constitutive equations, we can vary them with respect to the sources and get 2-point functions. So, and this is actually how we will derive Kubo relations later. So this is the formalism that we use, and probably many of you are familiar with. So since you're not stopping me, I'll just continue. I should maybe speed up a little bit. So the idea is there is also, just as a side note, what Ayan already mentioned in his introduction, there have been ideas to construct hydrodynamics from a more quantum field theory, or like even just a basic fundamental action principle. So just an idea that we have in physics, right? We want to construct all the dynamics from just a generating functional, and this can be done and has been started in these works here. I mean, there has been a lot of work on this, and this is not doing, this list of preferences is not doing it justice. I'm just mentioning this because that's where I was aware of this. There has been much more progress since this. But yeah, so this is just a side note. So now the idea is we want to construct these constitutive relations and somehow use the entropy current as a way to restrict them. So let me just illustrate how that works. And so this is the only calculation I have in here. So let me just at least go through that slide somewhat diligently. What I've written down for you is the divergence of the entropy current. We require that to be larger or equal to 0. What I've written down here is, as an example, ideal hydrodynamics. So if you just have the entropy that's carried with the fluid flow, that's your ideal hydrodynamic description for the entropy current. So there's no spins in here. Sorry about like I said that wrong. So this S is for entropy current, ideal entropy current. You have the current of charges with N that go with the fluid u mu, and then you have the energy momentum tensor in its only ideal fluid form, energy density and the pressure. And so this now we can calculate the divergence of this entropy current in ideal hydro, and that gives you this. You see that this capital D is here just the time-like derivative, right? That's what this is, because the u is a time-like vector. And now what we can use is we can use the first law of thermodynamics here in this form, and also use the current conservation equation, which we've seen before, in order to replace the ds here by the d epsilon dn. And with this equation, you also find that these other terms appear. So after this step, you can rephrase this by using the energy momentum tensor conservation equation, right? The energy momentum tensor is conserved. That's this equation, but we project it onto the fluid velocity. That actually gives us this equation here, because that was the form of the energy momentum tensor explicitly, and we have used this right here. The fluid velocity is just -1,0,0,0. That's what this fluid velocity is to 0th order without without any dissipative corrections. So now that gives me this form, and then in the last step, you can use the standard relation epsilon plus t is st plus mu n, and as you see, like factor out this divergence of u, and that is exactly what this is in brackets, right? That is 0. So this is what we learned from this little exercise, is how to think of this entropy current argument in more concrete terms. This ideal fluid produces no entropy automatically, and we just need to calculate the same, like perform the same types of manipulations. And what we need now is we need to be aware that there's some terms that are just not evaluating to 0, but that will potentially be larger or smaller than 0. And so then we have to find restrictions how to make these terms constrained, either by positivity of transport coefficients like conductivities or the shear viscosity of that type. We will see that those transport coefficients have to be positive because they multiply positive tensor structures in such an expression here. So for this to be true, they would have to be positive. And then we will see some other relations between transport coefficients emerge. So this is the context in which this happens. So here's the more general case. So the canonical energy momentum tensor is defined normally, including not only this ideal hydro part, entropy traveling with the fluid, but also a contribution from the current and the contribution from the energy momentum tensor. And so here are those contributions, just in addition to ideal hydro. Then you do the same thing, you calculate the divergence of the resulting entropy current, which is now the divergence of the canonical current up here, plus all possible pseudo vectors and pseudo tensors. And here's a bit of the magic. This is where, for example, Son and Sorovka found the extra terms that had to be added because of the chiral anomalies. So this is how the whole process, how it goes. And now this whole process needs to be done in first order formalism with torsion. Okay, good. So good thing is this, we already have introduced all the bits and pieces. So except for the first order formalism. So let me introduce this first order formalism pieces, which in part we've already introduced them. Maybe I should ask, are there any questions at this point? Okay, good. So everything we've just seen now with the in terms of the metric and so on, we now have to do this in terms of this first order formalism, which now instead of the metric we have the field line, and we have introduced in addition to that the spin connection as a geometric source. And this is very familiar to us in the context of Einstein-Cartan geometry or Einstein-Cartan gravity. So Cartan structure equations tell us, the first one told us that the covariant derivative acting on the field line gives us the torsion. So this is telling us also what components there are in. So this tells us that the field line and the spin connection are not independent. That's the one way, if there's torsion, one way to phrase this. Another equation, the second structure equation, is that for the spin connection, and it tells you that the covariant derivative of the spin connection is has this piece as well, and it's evaluating to the Riemann curvature tensor. And these are the two Cartan structure equations. The tetrad postulate is this postulate that this covariant derivative acting on the field line is equal to the standard partial derivative. Then it has an affine connection, and it has a spin connection piece. We have to be a bit careful because this affine connection here need not be just a Christoffel symbol, because this description should allow for torsion to be non-zero. If we were to use just the standard Christoffel symbol, then we will get this wrong, because we think of it as being given directly in terms of the metric components. That is not the case for this affine connection. So that's why I'm distinguishing it from what we know. This is not your regular Christoffel symbol. It's an affine connection which contains torsion contributions. And so you see that in here, this affine connection is not symmetric under exchange of the lower two indices. That is a non-zero torsion, the contribution there.
Question?
Yes.
The second Cartan equation, it holds in the presence of non-zero torsion also?
Yes,
okay.
It does, yeah.
Because the calculation of the curvature tensor becomes much more involved, right, in the presence of torsion. So
that's right. So I should say that the spin connection has a torsion-free part, like so, and it has a torsion part, like that you see on the right-hand side. So yes, you're absolutely right that this will, if I write this out in torsion-free pieces plus contorsion pieces, then this will look awful and difficult. But that's exactly where the torsion comes in form of this contorsion tensor, which is basically the contribution to the spin connection, which is there because of torsion.
Okay.
So that's a good point, but the structure is actually the same, no matter if it's with or without torsion. Yeah, good question. Thank you. Okay, so this tetrad postulate we obey because this is kind of on the same order of saying we want metric compatibility. That's kind of like a similar statement here in the first order formalism, and we are free to make that choice. And metric compatibility in particular, if we go back to the second order formalism with metrics, implies an anti-symmetry in the Lorentz indices for the spin connection. So this is also something that we like in order that we require in order to compare to the previous formalism. So these two, strictly speaking, are choices. The tetrad postulate and the metric compatibility are choices. Okay. So now we use all of that and apply it to in order to derive constitutive equations. So let's keep in mind what we're after here. So we originally talked about this in heavy ion collisions. So QCD would be the theory of interest that governs that type of experiment. So we have the quarks here. and everything's written in first order formalism with the vielbeins here contracted with the gamma matrices, and like the quarks. That's this the dynamical term here for the quarks. Here's the quark mass term. It's the quark mass matrix with the up, down, and so on masses on the diagonal, and we have the gluon fields here that contribute as well. Now, I guess this is the place where you could argue or ask, where's the spin orbit coupling, and so in a sense you have it in the covariant derivatives and the vielbeins. So the quarks carry spin, right, and there will be a coupling here between spin and orbital angular momentum here, and there's in particular here's the mass term which contributes to the linear momentum, to the or let's call it orbital angular momentum. So you see there's terms that couple spin and orbital angular momentum in this, and the operators that we're interested in. Let me start from the right because it's simpler. So this I should have put QCD here, so I will refer to that as SQCD to this action here. And the ones that we're interested in is the current, the charge current. So let's say a flavor current, for example, or baryon current. Then a spin current, as we said before, the spin current is defined with respect to variation with respect to the spin connection. And then we have the energy momentum tensor, which I now label theta, because right now I would like to define it as the variation of this the action with respect to the vielbein. So this is a slightly different energy momentum tensor, but I want to stay close to first order formalism. So this is the definition that I'm choosing.
One more question.
Yes.
So you're taking your connection and tetrad fields to be non-dynamically, right?
Say that again, the connection and
your spin connection and tetrad, you are taking them to be non-dynamical.
They're treated like background fields, like in quantum field theory, for example.
Right.
We always do that, like in the background field formalism is what you could think. Yeah.
Right. And otherwise you would have to include a metric Ricci scalar term in the action, right?
Mm-hmm, mm-hmm. Yeah, that's right.
No. I mean, I suppose maybe I'm moving too far ahead. But if you did make them dynamical, would that also, like, I mean, would it be possible to make them dynamical, or would that not be physical for something?
So I've thought about that. So I thought about it only in the context of building a holographic dual. So yeah, it's possible. And it's what you need to do if you want to do holography with these kinds of structures, right? Because you want, yeah, I mean, thanks for the question. So this gives me a chance to comment a little bit on why I think this is the right way to do this on the field theory side. That's because inspired by holography, what is this energy momentum tensor going to be? Well, we know that it's in principle its expectation value is the subleading term, the normalizable mode in the near boundary expansion of the ADS metric, right? Like of your metric in ADS space. And what will be the dynamical, or what will be the holographic representation of the spin current? Well, it will be the subleading term, like a normalizable mode of the spin connection, dynamical spin connection. And for that, you need non-trivial dynamics for both the spin connection in the bulk ADS spacetime and for the vielbein. And they might be coupled to each other, right? But at least we need to have a way, a formalism to write them down independently to begin with. And so yes, they will be dynamical in the holographic perspective, but here they are not. And so that's the answer that I can give you.
So this is the first step, right?
Say again?
This is the first step. I mean,
this is the first step. Right, and then I mean I've already done steps 2 and 3 towards holography, but it's not yeah, beyond that I would not be able to tell you anything more. I mean everything is working out. If you have torsion involved and you write these down, then you get equations of motion for E and for omega that are the equations of motion for them, and that you can expand near the boundary and perform holography with this.
Okay, thanks.
So that is possible. Yeah. Okay. Sorry guys. Yeah. I see I'm 1 hour and 5 minutes. So I will try to get to the point here. So conservation equations, you can think of them as.
Sorry, can I ask a small question?
Yeah, of course.
Yeah. Is there some kind of minimal coupling to spin connection, or?
Yeah, if you will, so then you could say this is my defining relation for what my covariant derivative is. So like the coupling that you mentioned comes in through just in terms of connection. So that is a minimal coupling, yes. So if this derivative acts on the quark field, like in this example right here, right, these two covariant derivatives D act on the quark or the antiquark.
Okay, I see.
And so these are coupling then the quark in this place here to the affine connection, which contains like this torsion piece here, right? And it couples the quark to this spin connection as we would expect for a Dirac action.
Yeah. Okay. Thanks. Otherwise, probably the spin current wouldn't be uniquely defined.
Yeah. Yeah. Yeah, I wouldn't know how to do that. Yeah, thank you for the question. Yeah. Okay, so let's see. So the conservation equations take on a slightly more complicated form if you keep torsion around. There are these pieces G mu, which are essentially torsion pieces, so like a trace of the torsion tensor. Sometimes I will also, as you note, as you see, I will contract the original torsion form of the torsion tensor with field binds such that you have Lorentz indices here, or like not local Lorentz, but you have the space-time coordinate indices here. So that's what has happened here. But this G is what modifies the torsion piece, modifies the covariant derivatives. So it turns out that these are the conservation equations that you get when you consider diffeomorphism invariance, local Lorentz invariance, and U1 gauge invariance respectively. And these are the conserved Noether currents, like for the energy momentum tensor, the spin current, and the charge current. So again, this is slightly more complicated, but maybe one thing to highlight here is something that people have also in heavy ion collisions talked a lot about, and that is kind of a fundamental result, is that you have a spin current. If you have a spin current and there's a non-vanishing divergence for it, that means you have a source, right, for a spin current. If you have a source for a spin current, that means that your energy momentum tensor needs to be antisymmetric. So if it's symmetric, then this source needs to vanish, right? That's what this equation tells us on a very fundamental basis. No, we haven't done any expansions in derivatives or anything. This is just a fundamental relation that you get by considering local Lorentz invariance. So that brings about the definition, like how is the energy momentum tensor correctly defined, and how is it not ambiguous, and how is the spin current not ambiguous. And you would see there would be transformations that I mentioned earlier, Bell-Infante transformations, or also they are called pseudo-gauge transformations that change the definition of sigma and that change the definition of theta. For example, from an antisymmetric theta, you can build a symmetric theta by that without changing these equations of motion. However, that changes the definitions of the currents and makes them ambiguous. So my claim is this is the right way of taking these currents and the conservation equations into account. That's because this is defined in a geometric way. And this is directly tied to the way that these equations of motion are derived.
So sorry, can I ask one more question?
Of course.
Yeah. Is there any pseudo-gauge transformation that will actually kill the source term here?
there have been papers where exactly such a such a gauge transformation has been written down. Yeah, yeah.
So if that is the case, then yeah, so defined spin current would be conserved, isn't it?
Actually, it needs to vanish. If I understood the literature correctly, that is what would be the consequence. The spin current would have to vanish in that case. I believe that is the last result in from a paper by Stefanov and Huang Yi and collaborators.
I see. Okay. Yeah. Thanks.
But as you see, I'm not a I don't think that this ambiguity should be there in the definition of currents, and I believe that there's a right way of defining these currents, and it's to some extent motivated by this microscopic Lagrangian, and then deriving the operators in, like, having a solid definition for what operator am I talking about. And when I talk about the spin current and energy momentum tensor, these are my definitions. Okay, so now the goal would be to write down the entropy current in first order formalism for a theory like this. And we have this in the back of our minds, but it's not necessarily restricted to QCD, this whole formalism. There's a lot of technology on this, and I will not go through this. I think I will go back to this. So this was the idea here, to show you something that you're familiar with, but to see it in first order formalism. So let me only point out the highlights here. One highlight is, instead of the hydrodynamic fields of temperature, or equivalently energy density, charge density, fluid velocity, we now also have spin density, which you can define if you dot the fluid velocity or project the spin current onto the fluid velocity. So basically pick out the Lorentz index time direction that's of the spin current, that's the spin density. And so that's now another hydrodynamic field. Another point is, of course, that hydrodynamic field sigma, the spin density, somehow needs to couple to a spin chemical potential in the first law of thermodynamics. So that is a contribution that shows up just like the chemical potential for a charge and the conserved charge here. And then you will see that the second law will take a certain form, which I will skip. I will just talk about the derivative counting, because this will be interesting. So initially I said that the derivative counting is, for us, that we're interested in scales of frequencies that are on the order of the spin decay rate. So this is the inverse of the spin relaxation time, gamma s. This is the spin decay rate, so to say. How fast does the spin relax? And so we're considered in that kind of regime. So our counting will be that the derivative counting is, the beta is the 1 over the temperature, inverse temperature, fluid velocity, chemical potential for flavor fields or baryons or so. That's the conserved current, and the field bind. Those are all of order 0 in derivatives, so no derivatives here. But the chemical potential and the for the spin and the associated spin density, and then also the spin connection, they are all of first order and derivatives. So that is the counting that you find, and I can motivate why that is the counting, but so just let me come to the conclusion. So you find constitutive relations when you perform this. These are the constitutive relations. It's a horrible mess to look at this slide. I apologize. I wanted to have a little more time, but in the interest of time, I will just again highlight what's important. So there's an ideal fluid here, which we've seen previously. This delta is a projector. It's defined down here. That's the projector, which is now defined with, instead of the metric, you have the field line and you have the fluid velocities. So that delta is still projecting on a space-like direction. And so that's giving the pressure contribution. So this whole thing is just the ideal fluid. Now here you have an interesting tensor structure. This is a shear viscosity tensor. So it's defined down here. It turns out to be containing the shear viscosity that we know and the bulk viscosity that we know. And if you work out these tensor structures, this collapses, this first term collapses to the standard shear term. So this will be the, if you want to rewrite this, this would be something like, in the simplest form, d mu u nu plus d nu u mu, and then minus the trace contribution. So this is what you would get from this. So, and times the shear viscosity times eta, and then minus the bulk viscosity times the divergence of the fluid velocity. That's what you would get from working out these tensor structures here. So this is the basic shear and bulk viscosity term. And then you have this additional one, which is the more interesting bit. So I'll show you that or discuss that. So you have this rotational viscosity, which has kind of a similar combination, but you see this this rotational viscosity tensor has the minus sign here instead of the plus sign. Otherwise, it's the same. So this is like a vorticity structure, because if the previous created something like the shear du plus du, this is du minus du, so a vorticity structure with a minus sign. So and so that is what multiplies the rotational viscosity in here. So it's governed by only one transport coefficient, the rotational viscosity. And that's what the extra contribution is. Of course, if you set the torsion to 0, T is the torsion in here as always, and the derivatives, they contain torsion contributions. If you set all of that to 0, this all collapses to our standard first order hydrodynamics that we know. Okay, good. So
Matthias, here in this rotational viscosity term, so like we subtract the trace part from the shear viscosity part, right? Yes, this part.
So here should, yeah, that's yeah, that's right.
So okay, this is antisymmetric, but in exchange, under exchange of mu nu and alpha beta, right? I mean, I'm wondering whether we have this. Do we need to add and subtract to have the trace part from here for this rotational viscosity?
Yeah, that's a good question.
Like rotational shear and rotational bulk, I'm just wondering. You know.
I mean, it's not what we find. So you're saying, should there be some sort of zeta s, yeah, right? Just by looking at the similarity of the tensor structures, it's a good question. I don't have an argument against it, except that it did not appear when we wrote this down this form. Good question. I have to think about it. It might have to do with the symmetry, that there's the sign difference leads to these contributions vanishing. But yeah, I have to think about it, because that's the major difference between the two terms.
Yes.
Okay, yeah, I'll have to think about it. Thanks for the question. Okay, good. So then the result that you get from this, when you vary this to this energy momentum tensor that we just calculated, theta xy, it's xy component in fact. When you vary it with respect to spin connection, this 0 xy component in particular, so you get a 2-point function between energy momentum tensor and spin current, and in that 2-point function you find this new this rotational viscosity eta s that I mentioned. There's a bit of a caveat here, because we talked about how we are not exactly having a conserved spin or spin charge. So the spin current is not really a conserved quantity. So that leads us to having to perform in the omega direction a limit, which is a restricted limit. So instead of just having omega going to 0, we need omega to be much larger than the spin relaxation rate, gamma s. And you see why. So if you look at the correlators that you get from the linear mode analysis, from linear response theory, you get a form that looks like this. So this gap term is normally not present if you have pure hydrodynamic modes. The hydrodynamic modes have a vanishing gap. So for them, for a hydrodynamic mode, gamma s would be 0. And then you would get from this type of formula, you get eta s directly. However, now there's this gap. And so this gap needs to be smaller than the frequency, so that the frequency is what survives in this denominator and cancels that frequency so that you get your eta s. This is the basic structure that leads to this restricted limit, and or like this is more illustrating how to apply this to the correlation functions that you get. The nice thing here is that this now allows us to compute rotational viscosity from microscopic theories, because if we have QCD and can calculate this correlator between the two currents, the XY component of the energy momentum tensor in QCD and the 0xy component of the spin current, then we can plug whatever our QCD result is, probably in perturbative QCD, can plug that in here and then take this type of limit, and that gives us a value for the spin, for the rotational viscosity, which governs the spin relaxation in this description. So that can. So
do you have to take an imaginary part here in the retarded?
Yeah. Yeah, that's a good point. It turns out that one doesn't have to do that. It turns out that you don't have to do it because it's just that the correlator just works out such that the cancellation looks pretty much like this. I like why that is so. We were thinking about that too. So there's other Kubo relations that we can write down, and those have similar Kubo relations or equations, but you need to take the imaginary part. So I have to think about why that was that you don't have to take any imaginary or real part. It just works out that way. I do remember that.
So there's a question also in the chat that is it a dissipative, right? I guess it is, right? Eta is a dissipative term or not?
That is a very good question.
Not necessarily.
I think in general the answer is yes, because we get a restriction from that the eta s needs to be larger or equal to 0 in order to satisfy the entropy argument. But what I'm interested in is the question: are there any terms from which in which eta s does not contribute to the entropy current? It's maybe some interesting terms that one can look at that describe non-dissipative transport that is connected with this new transport coefficient. So in all generality, eta s is connected to entropy production. But are there maybe some terms in some parts of the constitutive relations which don't contribute to entropy reduction and therefore are dissipationless transport? So that would be something that I would be interested in, because there is actually a relation to anomalies.
Okay, so it also appears in some equilibrium partition function. This eta s
yeah,
should also appear.
Yeah. Well, I think so. I haven't. That's a question that I haven't answered. This is something that I also started thinking about just recently.
And your thought about gravitational anomalies too? Gravitational or mixed anomalies in this context?
Not yet. No. I mean, this might be this might be very important here, and I can point. So there's a paper by Umut Gursoy and his former student Gallegos, and they looked at all the relations that arise when you do first order formalism and consider this in a holographic context. And so they find a lot of relations between anomalies and these effects that show up in like spin hydrodynamics or spin fluid dynamics as they write it down. Maybe this is a good point to yeah, let me, in the interest of time, skip this picture of eigenmodes. We kind of looked at that already before. The point was there that the eigenmode spectrum is altered and now contains the spin dispersion relations. Sorry. So if you want to know any more of that, then ask me. So instead, let me give you this idea here of fluid gravity. So this is the paper by Umut and his former student, and they have considered holographic spin liquids in the context of Lovelock gravity. So essentially, it's generalization of Gauss-Bonnet gravity, higher derivative corrections. It's written down in the Chern-Simons form of like a gravitational Chern-Simons terms, and then there's anomalies showing up there in that context, and as you would imagine for like something that you write down in some sort of Chern-Simons form, and then you can consider torsion-full first-order formalism, in like that's what they use in order to consider this whole thing. So it's exactly the appropriate way to like matching what we just looked at in the field theory. And then there's a deep relation to anomalous transports that shows up, that emerges. I don't have time to go into the details, I think, right now, but all that shows up there, and they lay out a nice fluid gravity framework to study these effects. And then the other point that I wanted to mention on the holographic previous work is we've calculated with my former graduate student Marcus, we calculated the hydrodynamic quasi-normal modes of rotating black holes. I mean, all quasi-normal modes, but we found there's hydrodynamic ones in these black holes. And this, so you have a rotating equilibrium state that's analytically known, and then you perturb around it, and you find hydrodynamic dispersion relations, and you find actually they are related to the dispersion relations at zero rotation analytically. So you can find analytic equations, and that means you also find analytic equations for your transport coefficients, so for shear viscosity and sound attenuation, sound speed, and so on. So they get corrections, and you can calculate this analytically in terms of the non-rotating values. So that brings me to future directions and to the end of this talk, really. You can perform fluid gravity for such rotating states. That would be an idea. So my understanding, I didn't understand even what happens when some plasma rotates and what is the fluid dynamics in the rotating plasma. So that's why we started out with generating a holographic model for a rotating plasma. That was the idea of this work. So, but now you could, instead of having a global rotation, well, turns out even in this model you have vorticity, which is more complicated than just rigid rotation. So this is actually a quite intricate system when you think about it a little longer. But what you can do is you can make now these rotating black holes. They have angular momenta 2 in ADS5. So these two angular momenta you can make now position dependent, like in the fluid gravity sense. So these parameters of your black hole now become parameters in the gradient expansion in terms of fluid gravity. So you have locally, you have angular momenta in your description, and can match that to a hydrodynamic description, build constitutive equations. So that would be a suggestion. And then obviously you can consider a probe fermion in the rotating background here, and consider that as one like a model for a hyperon in heavy ion collisions in a plasma, and ask how is it affected by the plasma? How is it interacting? What is its relaxation time? When you polarize the plasma, for example, and how long does it take for it to flip? So you can ask such questions. Then there's you can derive and test the spin hydrodynamic constitutive relations and Kubo relations that we have derived in or that have been derived actually in the literature previously. So one example is you can plug the holographic correlators that you calculate in your favorite model into Kubo equations that we've just derived, right? And calculate the spin vorticity, this rotational viscosity is what I meant to say. You can compute and compare equilibrium states with including spin, and compute quasi-normal modes and compare to the spin hydrodispersion relations that I just skipped, right? So the spin hydro has certain dispersion relations, and one can calculate quasi-normal modes in holographic models and see how the spin dispersion relations would look like there. Calculate the holographic correlation functions and use the Green-Kubo formula. Obviously, is the easiest thing to do, and then include magnetic fields, chiral anomaly, charge densities, you name it. So there's a lot to do, I think, a lot of fundamental work and a lot of fundamental insight that holography can bring to the table there. Pretty much that is what is on the summary slide. We have fundamental, or we would like to understand better on a fundamental level how spin is showing up in hydrodynamics, how to include it in hydrodynamics. And there's a need to describe existing experiments, heavy ion and condensed matter experiments. So fundamentally and experimentally both interesting to extend spin hydrodynamics like on the holographic fields, like just study it holographically and understand it better. So with that, thank you very much for your attention, and sorry for the overtime.
Okay, thanks a lot for this nice talk. It's already been a little late, so maybe we can take a few questions. Yeah, Shamapan, please ask.
Yeah, so I was wondering whether this spin modes, they are also some sort of non-hydrodynamic modes, right? Hello?
Yeah, sorry, I'm thinking about your question. You say magnon hydrodynamic modes?
No, spin modes, they are also non-hydrodynamic modes.
Oh, yes, they are. That's correct. So like, for example, here we see that the imaginary part of the parallel spin mode is gapped, right? There's a gap here in the imaginary direction. And here you see that that is true also in the transverse spin mode. So they are gapped in contrast to all the hydrodynamic modes. So and the spin gap is as you see here is governed by this gamma s, by the spin relaxation rate, and over here as well. So that's gamma s, and that gamma s is related to the spin susceptibility chi s, and the rotational viscosity eta s.
Okay.
So it is gapped, yes, and thereby it's non-hydrodynamic, but it is among the fast modes, it is the slowest.
Okay.
So we don't have to worry. So usually, for having non-hydrodynamic modes, we have a causal theory. So I'm just wondering whether we have to worry about a causality appearing in a causal modes appearing in, or ensemble modes appearing with distributive spin hydro.
Whoa, you're opening a can of worms there. Yes. Yes, we should definitely. So, and we should not. So we should worry about acausality to the same degree as we worry about acausality in standard hydrodynamics. Because like the way I would think of it is hydrodynamics is causal. It's just that if we decide to write it down in a particular way, then we sacrifice causality for ease of notation. So I would say if you write down hydrodynamics in a general frame, then you would not encounter any superluminal modes or anything like that. It just depends on what you call hydrodynamics, I think. So if you insist on truncating a series and then claim and then complain that it has problems, well, you should not have truncated it. I'll let you come to your question.
Yes. So what I wanted to ask is, when we cure hydro of the causality problem, we introduce non-hydro modes. But we
You're
already
thinking
have,
of Miller-Israel-Stewart
Yes,
theory,
yes.
adding, which is very similar to. So I think that's important to recognize as you do. Like this, what we're doing is very similar to Miller-Israel-Stewart in the sense that also in Miller-Israel-Stewart you're adding an extra degrees of freedom to your hydrodynamic theory, and claim that these are slow.
Right. So then this should be causal, right? I mean, this is what because you have these non-hydro modes, which I mean, I'm well, it's difficult to hear.
Yeah, so this is very similar to Miller-Israel-Stewart in the sense that, yeah, I mean, you can rewrite this as 1/tau s, right? So in that sense, it shows up in a similar way. Like there's a relaxation time. Gamma s is 1 over a relaxation time.
Yeah.
And it creates a new mode in the spectrum that yeah. So I have not thought about, I haven't tested causality of this form of spin hydrodynamics. We have chosen the Landau-Lifshitz frame to work in, and thinking about those questions would be a next step. So I'm hesitating to make a solid statement, because I don't know how reliable it will be. I can tell you what I would expect. I would expect that similar things happen just like in the standard hydro description. And is it exactly like Miller-Israel-Stewart? I don't know in terms of causality, because I just haven't tested it. But just based on your arguments, that seems reasonable.
Thanks.
Great. Can I ask a question?
Yeah, of course.
Yeah. So, so I was just wondering, since this spin mode, there's a gap for the spin mode, then isn't it that all the hydro modes up to this particular gap one has to consider, right?
Yes.
So if that is the case, then isn't it that some kind of non-universal features also can enter there?
How would non-universal features enter, except for like by the spin mode?
No, usually we would probably be interested in dispersion in the limit when k goes to 0, right?
Mm-hmm.
So if you have to run it up to this gap, then I mean, it is not clear to me whether in this particular system whether there are some non-universal features of this QCD will show up, or
are you worried about the Kubo relation?
I think he's basically asking about whether spin hydrodynamics is universal or not, because you're taking it to be the only gapped mode, that only softly gapped mode. Whether there could be other softly gapped modes or not. I think that's the question.
Oh,
right?
yeah. I mean, it's universal in its regime of applicability, right? So I mean, this is evading the question a little bit, but I said that I want this to be valid in a certain range of frequencies, and so by adding these spin hydro mode, you're absolutely right. I mean, that's my choice. I like all the dynamics that is beyond hydrodynamics is in the spin modes, and that's the only physics I add to it. And I mean, but then like if there's no other modes in this regime, then that's I would call those the universal results of spin hydrodynamics that are produced by this. So it's universal within its regime of applicability. These other modes, they can come in, of course, by like because in different systems they come in different ways. Yeah, other fast modes can become slow if you have quark masses or whatever is like making certain modes slow. And then they are in this regime, and then they would affect the results and predictions of spin hydro. Because then I would have to take whatever other slow modes come into this regime, I would have to take them into account. So maybe that's what you're asking. So so then I can apply spin hydrodynamics in the form that I've proposed it to theories where spin modes are the only slow modes on this scale. Or regimes of theories where that is the case.
I mean, what I was wondering was if you look at the traditional hydro modes, there probably we end up using these viscous coefficients and so on, and we don't consider them to be functions of k, the wave number, right? So if one has to go up to this particular limit, then probably these specific functions have to be defined, and those are the non-universal features which I was trying to. I was just wondering whether such. Yeah.
Here also you are taking limit k goes to 0 first, right? In order to define it as.
Well, in order to define it as, so there's a lot of things that come in that are connected to what you just mentioned. So first of all, you can and people have calculated the k dependence and the omega dependence of these transport coefficients, like shear viscosity, for example, or also conductivities. I mean, we know that from electrodynamics, like frequency-dependent conductivities, but you can also calculate momentum vector, wave vector dependent conductivities. And what that would give you is essentially like a decay width, or like a length scale over which your charge distribution would survive. Compared to a relaxation time, which you get when you take this frequency dependence. So those kinds of quantities you can calculate. In terms of universality, I still don't quite understand what you're after, right? So because I try to say, like, yes, if at any point in I mean, you always have that problem, right? So if at any point you are in a regime of, let's say, a heavy ion collision, where other fast modes come into your pure hydro regime, then your hydrodynamic predictions will not be valid anymore. So for example, that happens near the QCD critical point, we believe, because near the QCD critical point, there are, is it called critical slowing down, and you have mode excitations on all length scales, so your correlation length diverges. Near the critical point, hydrodynamics breaks down in the QCD phase diagram. So one has to do something else there. And so in that sense, it's not a universal description of systems that are governed by QCD.
Okay, I think we have to move on. So because it's already too late. Maybe if there is some other kind of question, we take it now. Actually, I also have a very short question on this, like in the holographic point of view, you have this, so there are some relations about how much angular momentum a black hole can carry compared to the mass, otherwise you have naked singularities and stuff like that. So so do you find some kind of, is it some kind of reflection of it in the spin hydrodynamics? It should reflect somehow, or do you think it is something universal, or it should be something very special to holographic systems? That's kind of limits.
You mean extremal limits?
Yeah.
So for the rotating black holes, I mean, that's something that we calculated and carried out in this analysis. So your equilibrium state is stable and totally fine up to stable against fluctuations up to extremality. So you can, so that's something that we've shown here. So the dual hydrodynamic rotating state with sound modes and shear diffusion modes is stable up to extremality, and then
I'm saying that the fact that there will be instability is a holographic feature, right? That if you once you go beyond the extremal limit, that you have this instability, or you can have a potential that should be some sort of a holographic feature of the system in some way. No, I mean,
yeah,
do you think it is something more general?
Oh, I see. So I was thinking that it has to do with eventually with. I mean, this is too naive, but just when you spin it too fast, at some point you have causality violation, that kind of limit.
Or you think it's that simple as that? And
so let me be more careful. So let me, instead of calling it causality violation, I think what you need. So yeah, okay. I have an example that might be explaining exactly what you're asking for. So we know that there is such a limit in just field theory when you look at a rotating fluid, and this is in the appendix of our paper. The fluid profile can be given by this form here. Omega is a constant, and so the fluid velocity is describing a vortical fluid or like a rotational fluid. You can calculate what the temperature dependence is in such an equilibrium state. It's this. And the point is, in order to spin this such that it spins and violates causality at the boundary of this, like a disk shape that you can imagine here rotating around the z direction, in order to reach that limit, you would need an infinite angular momentum. So you can, like, that's basically the upshot here. You would need an infinite angular momentum in order to spin this fast enough to violate causality. And so this is this is too much. You cannot give anything an infinite angular momentum. So that is basically an example where where you have a flow which addresses your question. So in a fluid, there is such a boundary. Given a certain energy, you have only so much angular momentum, or vice versa.
Okay, yeah, that's quite natural then. Yeah, that should be very general. So if you take this kind of extremal limit where you should get like with the maximal possible angular momentum, you will expect that the near horizon region would be something like a curve CFT like description. And exactly. You would expect some nice simple description to emerge in this overspinning limit.
Yeah, I agree. I mean, nice in a certain sense, but then also you have a double singularity at the horizon. So yeah, so there's this. I think there's like also a lot to be done in that from that direction. Just start at the extremal case, as you say, and then describe holographically what happens there. Consider transport in that. So because you can still do that. I mean, the temperature will be 0, but you can still perform an expansion in gradients, and you have other scales like the angular momentum in that case, right? So then you can relate the gradients to how small are they compared to the size of the angular momentum.
The T much less than omega, some limit of that kind. This is some temperature.
Yeah, exactly. Yeah. So I think that would be interesting to. We talked about it a little bit. Marcus Gabiso Amano, my former graduate student, soon to be postdoc in Henan. Like he and I talked about this quite a bit, and he looked a little bit at the literature. But it's been a while, so that like he would be a good person to ask about this.
Okay. Yeah, it has been long. I think we should. Yeah, it was quite interesting. Thanks for giving this talk and staying over for this for a discussion. And hope you will visit us in Chennai.
Yeah, same here. Like, let me know if you're in the country. I'm very happy to have you visit and show you around.
Great. Okay, so
Thank
have
you.
a very nice day and a very good cup of coffee. And we finished your game.
Thank you very
Yeah.
much.
So, yeah. Okay, so
Bye.
see you. Bye. Bye to everybody.